We are going to be talking about the Black-Scholes model. The deal with the Black-Scholes model is it's going to use the same tools that we had in the binomial model, which was delta hedging as well as no arbitrage. Only thing, the language is going to be different. The maths is going to be different. Also, we'll be considering dividends as well as options on the future, on futures. Okay. Thing is, the Black-Scholes model comes with assumptions. With the binomial model, the assumption was the price would have either risen or decreased only to two values. Increased one value, decreased two values. Black-Scholes model also has assumptions, and these assumptions can be shown to be wrong, but the model is still useful. As far as an option goes, it will be depending upon the asset price and time. Then these basically are the variance and the drift of the asset, and then this thing is the expiry, this is the exercise price, and this thing is the expiry, as well as the interest rate. Okay, but when we're going to be talking about options, we would generally write it as just V as a function of asset price and the time at which you're looking at. Thanks. Okay. So in order to construct, what we do, we basically first try to get rid of the randomness. Okay, the way to do it is construct a portfolio where we are longing an option and shorting a stock. The delta has to be determined such that the randomness vanishes, and we'll be assuming log normal walk. So there is a drift term and then there's a variance. We have been looking at it before also, and we saw that for a log normal walk, any function of the asset is going to have a time change, a partial derivative with respect to time, partial derivative with respect to the option, as well as something which is squared, sigma squared s squared dt, and the second derivative with respect to the asset price. Okay, having that, the portfolio that is there, that itself is going to change with this term minus delta times ts. That is the minus delta times ts. Okay, the only random component that is there in this expression is ds. dt is not random anywhere. So if you want to get rid of the random component, what we say is we put delta is equal to dv by ds. Okay, so this thing removes the randomness. Then we are going to be having that the portfolio that is there is just a function of time change. It's just basically changing as a function of time. There is no randomness. Something that is not random is basically cash, which you can basically put in the bank. If you had instead taken this particular portfolio, exchange it for cash, and then put it inside a bank, the interest that it will incur is going to be R. So this is the amount of interest that you're going to be getting. No arbitrage implies this has to be equal to this. How to see that is the case? In case this is higher than this, what you could do is you could just take the the value of the portfolio that is there in rupees, take that much amount from the bank, buy up the portfolio. Okay, then in time delta t, this is the amount it will change. Okay, the R delta t that is there is the interest rate you return to the bank. You'll be ending up with this risk-free profit. Okay, so because you're ending with the risk-free profit, this cannot be greater or it cannot even be smaller. It has to be equal. That basically gives you, substituting the fact that using this expression we are ending up with this expression, and then we just substitute the value of the portfolio, which was v minus delta s, and what we end up with is the Black-Scholes equation. Okay, now one thing you can easily note over here is that there is no role for the drift. The drift has disappeared. Okay, there's only an interest rate that is there as well as the variance that is there. Okay, another thing to note is that because v minus del v by s, okay, this behaves like cash, right? Because that is the portfolio, which is, it doesn't have any randomness, and anything that is not random could be like considered as like cash. That is why we could use a no arbitrage argument. The idea is that cash plus this stuff basically behaves like an option. Okay, so this thing is you could just replace an option in your portfolio with cash plus this particular number of assets. Okay, so this is what it's called by a complete market. This is something that we also saw in the binomial model, where given a cash, in case of we having a basket of cash options and the asset, we could just take any two of them in the basket and then construct something which will be replacement for the third. Okay. Now, in case, just giving you a flavor of how to solve this Black-Scholes equation backwards, which is called the explicit finite difference method. Okay, the thing is, at expiry, in case we are looking at a call option, we know that the value of the option that is there is just the maximum value of this asset price minus the delivery price, comma 0. So it is equal to S minus E if the asset price is greater than the delivery price, or equal to 0 in case we are in the opposite direction. Okay, so the thing is, this is what we are having the status of the option value at expiry. Based on that, we can evaluate the first and second derivatives. Just look at this. We can see that the first derivative is just 1 for s greater than e and 0 when it's s smaller than e. On top of that, for s greater than e smaller than e, because the first derivative is constant, second derivative is equal to 0. Okay. That being said, the Black-Scholes at expiry, if we are just going to take these numbers and then going to plug them in inside the Black-Scholes equation at expiry, we know the second derivative is 0, whereas the first derivative that is there has some specific terms. So let us consider when s is greater than e. When s is greater than e, this is equal to 1. So make the substitution. When you make the substitution, you're getting del v by del t plus the term which was multiplying del v by ds, which is equal to 1, minus r times the value of the option at expiry, s minus e, is equal to 0. This then gives you an expression for the partial derivative of v with respect to t, okay, which is just equal to minus r times e. Okay, once you're getting the partial derivative, you can evaluate what is the value of the option at an infinitesimal small time delta t before expiry. Just solve this expression. So we can do that. Okay, and since we can do that, what we can do is we can evaluate the value of the option at small time interval dt before expiry for s greater than e. Do the same thing for s smaller than e. These things will be taking on different values. Okay, and then you can again evaluate v as a function of t at a value t minus dt. Once you have got the value of v at t minus dt, repeat. Evaluate dv by ds and these two terms at t minus dt, and then evaluate the expression for dv by dt, and then evaluate the value of v at t minus 2 dt. And this way you can just continue backwards, okay, until when the option was basically set up. Okay. Now, certain things went inside the assumptions that we had done in the Black-Scholes model. One was obvious that the asset follows a log random walk, but the idea is that, you know, t, the sigma phi that is there, the sigma that is there, what we had considered was time independent, it could be time dependent. Okay. Next, the risk-free interest rate may be a known function of, what we have assumed is that it's constant, but we could also have assumed that it was a known function of time. However, the issue is that this interest rate itself is stochastic. Okay, so that basically changes, how the value of the option should basically be priced. Okay, and that is, breaks down the assumption of the Black-Scholes model. Another very important thing that we had done is delta hedging is done continuously. See, the thing is, what we did is, we constructed a portfolio, and we are seeing how the portfolio changes in a small time delta t, and you're looking at a limit delta t going smaller than 0. Okay, the assumption is that, in order to get into this argument whether people can basically use arbitrage arguments to make money, okay, there is an assumption that, okay, possibly somebody could be doing this in the market. Okay, but the problem is that in the market you cannot be delta hedging continuously, it is only done discretely. Okay, the thing is, because the main reason is that whenever you're having an asset, the thing is, at every instant, your dv by ds is going to change. Okay, so at every instant, supposedly somebody is changing the value of the short that is getting stocked, that is getting shorted. But just shorting a particular stock, the transaction itself costs money. Okay, so then depending upon how much the transaction cost is, you might either have frequent hedging or non-frequent hedging. Okay, and that is the reason, we have to, that is going to set the time between the hedging. and then that is also you know factoring in the transaction cost. That is going to completely change how this delta hedging is done. It is first of all being done discretely, but whereas we have assumed that it's being done continuously to get the Black-Scholes equation. Okay. So these are the assumptions. There is this assumptions of no arbitrage opportunities. Let me just not consider this right now. Okay. Next, as far as the option went, right, we have not assumed whether it is a call or a put option. The assumption of whether it's a call or put is basically understood by what is the value of the option at expiry. Okay, so this thing is called the final condition. You know, that is going to be setting up the final condition, you know, whether it's a call or a put. And as we had seen when we are looking at the way of solving this expression, the final condition is which is utilized to go back and start solving things numerically. Okay, so the Black-Scholes expression that is there, in order to solve it, you will also have to utilize this final condition, okay, on your option. Okay, now consider options which give dividends, on options on assets which are giving dividends. Assume that, you know, the asset is such that the holder of the asset will receive a dividend D, which is continuous and has constant yield D. That means in time dt, the holder will receive an amount D times S times dt. Okay. That being said, what we have is when we are considering a portfolio, okay, the thing is, because I have an asset S with me, okay, that means I have borrowed this particular asset. Since this asset is giving a dividend ds dt, I basically have to give this much amount of dividend. I'll be owing this much amount of a dividend. Okay, so this is the amount that I'll be removing from my portfolio in a time dt. So this is what my value of the portfolio is at a time dt, the original stuff that you had minus the stuff from the dividend. Okay, so once we have that, we take that particular quantity and then we make a substitution, and what we find is that this is the value that you get for this is the answer that you get for the dividend paying option. This is the Black-Scholes equation that is obeyed for dividend paying options. Similarly, if you had considered currency options are basically options on a foreign currency which give you an interest rate RF, okay, continuously calculated interest rate RF. This thing is just almost like the foreign currency. If you consider the foreign currency to be an asset, it is giving you a dividend equal to RF. So because of that, the Black-Scholes equation for this currency asset, currency option, is basically just going to be what you had over here for the dividend paying option, replace the dividend by RF. Okay. Finally, if you consider commodity options, there is something different that is happening there. In the question of a commodity, the holder of the commodity loses money, okay, because he has to pay money to store that particular commodity. This is unlike an asset paying dividends where the holder of the asset gains money, which is the dividends. Over here there is a loss of money. Okay, so if we consider Q as the storage cost per unit commodity per unit time, then inside the option, wherever there was a value of D, wherever there was a D, you basically substitute a minus Q there. So that is why you're going to get this as R plus Q. Okay, wherever there is a D, you substitute minus Q. Okay, so this is the way you would be pricing commodity points options. Okay, now just let's get back to the expectations. Okay, when we were talking about expectations as a way of pricing options in the binomial model, what we had is that we had a particular asset which could go to upwards to a value US, or it could go downwards to a value VS. Okay, the probabilities were set as P and 1 minus P. And in case and then afterwards, you know, we had this variance, you know, this U and V would be depending on the variance because they're telling you how much is the fluctuation in the asset value. And P that is there would have been dependent upon the drift, because that is going to be telling you what is the mean change. You know, that thing is going to be telling you, in case you're looking at the mean change in the value from here to here, okay, how is it going to be dependent on dt. Okay, now once we had that, the option that was there, we know the option could either go up or it could be going down. Okay, if we assume that it went up with the value Vt and went down with the value V minus, how is that related to the value V? We had evaluated an expression and found that the value that is there is having a form which is like this. It is almost like you're evaluating the expected value of the option using probabilities which are not the real probability to go up or down, but which is the risk neutral probability, where the drift has been replaced by the interest rate. Okay, so to write it up in terms of expectations, the expectation was that you are evaluating a risk neutral expectation of the payoff function, assuming a risk neutral it's a risk neutral expectation. That is, you're not basically evaluating the expectation using using the actual probability, but a risk neutral probability. Okay, and that is why the u that was there was substituted by an r. That is why the u never appeared in the binomial distribution, in the binomial pricing of the model. Okay, similarly the mu doesn't appear, the drift doesn't appear in the Black-Scholes model. Okay, the real random walk, when we are considering a real random walk, okay, when we are considering a real random walk, we are having an actual random walk which has a drift mu and a variance phi. So when we are evaluating the option using expectations, what we consider instead is an artificial random walk. Okay, an artificial random walk where the drift is r and the variance is sigma. Okay, this thing never exists, but it's an artificial random walk. Once you're using the artificial random walk, then you can consider the payoff. Okay, using this artificial random walk, what is the value of the using the artificial random walk, you will get a probability distribution for what values the asset is going to be taking in the future. Using those particular values, what you will do is you will be evaluating you'll be having a probability distribution for these particular values. From that probability distribution, you will be evaluating the expected payoff, and you are going to be discounting that with the interest payments, with the interest rate. Sorry. Okay. So that is why you don't have the conception of the drift in the actual evaluation of the option value. Okay. Now the another thing that is there is, we have been talking about no arbitrage arguments. No arbitrage was used in the binomial distribution and the Black-Scholes also. Turns out that it is only in these two particular models that you could use no arbitrage arguments. Just to give a small example, if there was a trinomial model where the asset basically took on 3 values at the next time step, then if you constructed a portfolio, okay, the portfolio also would be having 3 different values, okay, at the next time step. In the binomial model, what we did is we equalized the you had 2 values, you equalized the 2 values, and that gave you a value of delta. That is how we had basically hedged this particular option. If you want to hedge a trinomial option, all 3 of these will have to be put equal to each other. But you cannot put all 3 of them equal to each other because you're having 2 equations and just one unknown. So you can't use delta hedging for a trinomial model. So it turns out that Black-Scholes and binomials are some specific models where you could basically delta hedge and use no arbitrage arguments to price the options. Okay. Now let us consider some other valuations using the Black-Scholes techniques. Okay, let us be considering forward contracts. Forward contracts are what? The idea is that when you enter into a forward contract, you will be buying an option, or you'll be buying an asset at a fixed delivery price S bar at a time t in the future. Okay, this is the option. This is what a forward contract is. Okay, it doesn't give you the option to buy, but it gives you the right to buy. That is, you have to buy. Okay, or it gives you the obligation to buy. It doesn't give you the right to buy, it gives you an obligation to buy. Okay, now in order to price this kind of a contract, what we will do is we'll construct a portfolio again, where V is the value of the forward contract minus delta times S. Okay, use again no arbitrage over delta t, and then you will end up with a Black-Scholes expression. Nothing special up to here. Okay, the point that is special is the final condition, because this is an obligation to buy, not a right to buy. The payoff that is there is just going to be the asset value minus how much minus delivery price. Okay, now this thing becomes much more simpler to solve exactly, because if you are using an expression like this, S minus S bar E minus R T minus T, you can see that it solves this boundary condition, because the T is equal to big T. This is what you get, and you take this and you plug it in over here, it solves this expression also. Okay, so let us go back to how we had valued a forward price, a forward contract of a forward price in chapter 1. What we had said is that, let us say that at today's time, small t, we got into a forward contract. and then we shorted an asset, and we took that asset, and the money that we got, we went and put it inside a bank. Shorting of the asset implies that you're having minus S in your portfolio. Putting it in the bank is just plus ST. Price, you are saying that at time when you got inside the contract, there was no value added to the contract, and the total value is basically equal to zero, because it doesn't, the total value of this portfolio is zero. At maturity, at big T, what you have is the value of the contract is S minus big S. Okay, and then what you're having is the following. What you're having is minus S, the asset that is there, the shorted asset just is the shorted asset, and the money you put inside the bank has got an compounded interest. Since the value of this particular portfolio is equal to 0, what we can do is we can just solve for it, and we get that the delivery price is ST e raised to R t minus t. Okay, now the thing is, with the Black-Scholes model, what we had is that the price of the forward contract is S minus S hat e R t minus t. But as in order to make sense with this, the idea is that we got into the forward contract, the price of the forward contract was 0. So this thing is saying that when you this particular value at time t, that is when the contract was initiated, the value had to be equal to 0. So this value is equal to 0. Because it's equal to 0, what we have is that the delivery price gives you the same value that we have here. Okay. Now we will construct future contracts. We'll be considering future contracts. Future contracts, with the idea is like they are forward contracts, but they are settled every day to make sure that at the end of the day, the price of the contract is equal to 0. That is, say that you own a future contract with a delivery price F, okay, RS. Okay. Now if these futures that are there, okay, they become F plus delta rupees, okay, then you will be paying the absolute value of delta to the guy who is writing the contract. Okay, that is the guy from whom you will be buying the asset in the future, equal to delta. Okay, so that there is no profit made on a particular day. Okay, similarly the writer pays you delta amount, absolute value of delta amount, if delta is smaller than 0, so that you're not holding a loss at that particular day just for holding the contract. Okay, so the future contracts are settled daily to make sure that the writer as well as the person who has the contract, they are not making losses at the end of the day. Now if that is the case, how do we price this asset? Again, we construct a portfolio, longer future plus shorter asset. When we started at the morning, our asset basically had a value. The value of the asset is equal, value of the future is equal to 0 minus delta S. Okay, this is what your portfolio is. By the evening, what happens is that the future has basically changed in value, delta F. Okay, because the future has changed in value, delta F, basically what you have to do is you basically will be gaining. Say the future has, or let us say that F that is there is the delta F is basically the money that you gain, and that is at the end of the day, what is happening is you are taking a contract. The futures are basically getting settled. Okay, let us say that in the settling you make money equal to delta F. So that means that delta F gets added to your portfolio. So the change in the value of the portfolio is delta F minus delta F minus delta ds. Okay, now what we have is, let us expand this df. Df expanded for a log normal random walk has a form like this. We have been seeing that again and again. This thing is minus delta s, plug delta is equal to df by ds to remove the fluctuation, because then there is no fluctuation here. No arbitrage would imply that this is equal to r pi dt. Substitute the value of pi. Once you substitute the value of pi, what you get is the following expression. Okay. As far as the boundary condition goes, that is, that the final condition goes, the future that is there at the end of the expiry, because there has to be made no profit at the end of the expiry, what you should be having is that the future price should basically equal to asset price, because the futures are basically valued at equal to 0 throughout the contract. Okay, so because we are having the final price f s of t is equal to s, if we make that substitution with this final condition, we see that this solution works. and this thing is actually the solution that we had also had when we are considering the, so this thing is the price of a future contract.